In last few classes, we started discussing over iterative methods, and I have given you some introduction to basic iterative methods and also worked on their convergence analysis, which are Gauss-Seidel and Jacobi based methods. And later we have seen that convergence rate of these methods can be improved using certain methodology called successive over relaxation. However, what we have seen there is that these methods are restricted only for diagonally dominant or irreducibly diagonally dominant matrices. That is, the diagonal term in its absolute value must be greater than equal to sum of all the off diagonal terms in their absolute values, and at least for one row the diagonal terms absolute value is greater than, not greater than, equal to, is greater than sum of the absolute values of all the off diagonal terms. Only for these cases the matrices Jacobian, Gauss-Seidel or successive over relaxation can give a solution. And we have seen that if we take a diagonally dominant matrix and if we do a row permutation, the solution still remains same. However, the matrix changes, but Jacobi or Gauss-Seidel fails for that. So, there is a particular restriction on Jacobi and Gauss-Seidel, and the convergence rate depends on what is the maximum eigenvalue or the spectral radius of the iteration matrix G. That cannot be greater than 1. If it is less than 1, then only the method will converge, and that shows that it will converge for any diagonally dominant or irreducibly diagonally dominant matrix. However, if the maximum eigenvalue is large, is less than 1, but still large, the convergence rate will be slow, and we can only improve the convergence rate using successive over relaxation technique. Even there is a optimum value of omega or over relaxation factor based on which we can get highest convergence rate. And if we will later discuss about a number of iterative methods, if we compare like optimum omega successive over relaxation Gauss-Seidel with a faster iterative solution technology, we will see that Gauss-Seidel or SOR Gauss-Seidel is still way slower than these faster iterative solvers. Those solvers we will discuss. So, the basic problem with Gauss-Seidel and Jacobi iterations are in twofold. One is that they are restricted only for diagonally dominant or irreducibly diagonally dominant matrix, and another issue is that their convergence rate is limited by the maximum value of the spectral or maximum value of the maximum eigenvalue of the iteration matrix or spectral radius of iteration matrix. If it is large, even using successive over relaxation, we cannot increase it to increase the convergence rate to a very high extent. There is an optimum omega for which it will be maximum. So, there is some restriction on the convergence rate, or there is some restriction on the number of iterations that is to be performed for solving a matrix using Gauss-Seidel or Jacobi or SOR Gauss-Seidel. So, now we think of looking into faster solvers. That is the very importance of this particular course is that how can we solve large equation system using iterative methods which give us fast solution. So, when we start looking into faster solution, we have seen that beyond SOR Gauss-Seidel is restricted. So, we look for some other solution techniques, and these solutions techniques will not be direct solution techniques. So, that means that I will start with any arbitrary x 0 and only use that particular equation x is equal to b, substitute guess value x 0 and update x. These direct iterative techniques are restricted in terms of their applicability for diagonally dominant matrix as well as in terms of the convergence rate or speed of the solution. So, we look for some other iterative techniques, and what we start discussion of these other, from here we will start discussion on other iterative techniques, and a class of techniques named Krylov space will follow later from this discussion only. So, we will start discussion with projection based iterative methods, and this with the particular method I will try to discuss in this 1 or 2 sessions is steepest descent method. So, this is also known as gradient descent or gradient search method. So, if we look into this method, it starts with the theorem. Suppose there is a symmetric and positive definite matrix A and B is a vector, and now we define a quadratic functional J. A quadratic functional means it is basically a quadratic function in which all the components of the vector x is associated. X is a vector of same order as B. So, this quadratic function is defined as Jx is half x transpose Ax minus x transpose B. If we can define this function Jx, then x star is equal to B will imply that Jx star for any value of x star, Jx star is less than Jx for all x which is not is equal to x star. So, this basically says that if we can define a functional half x transpose x minus x transpose B, we can say that x star is equal to B, where we will get x star is equal to B for that particular x value of x star, Jx star is less than all Jx or Jx star is a minima. So, if we think x to be a single valued vector of dimension 1, and we write that this is x and this is Jx. So, this is the Jx functional, and here at x is equal to x star, Jx star is less than any other Jx. This is the minima, or we can say that this is minima of Jx, and at this particular x is equal to x star location, Ax star is equal to B, or Ax star is equal to B is a solution. X star is equal to B gives us the solution is x star is only where Jx is minima. Instead of solving x star is equal to B, now we can try to find out minima of Jx. That is the main philosophy behind this method. The converse is true. That means, if we find out a minima of Jx, that is Jx star is equal to Jx for all x which is not x is equal to x star. So, for one particular x star I get a value of Jx star which is minima, then at that x star is equal to B. So, when we write for all x not is equal to x star, all x not is equal to x star, that says that there is one particular x star for which this is solvable. So, this equation system obviously has a unique solution. So, what this theorem mean? That a matrix solution methodology Ax is equal to B, I have to solve this. This can be replaced by finding out minima of Jx. If we can define a function Jx is equal to half of x transpose x minus x transpose B and try find minima of Jx, the minima is the point where Ax star is equal to B is satisfied. So, matrix solution methodology can be posed as a problem of minimization of a multivariable quadratic function. Instead of solving x star is equal to B, x is equal to B, we will find the minima of Jx, and that is why this is sometimes called also search algorithm, gradient search algorithm. We will look into the gradient method later, because minima is associated with gradient in a sense. So, so the idea is that instead of solving x is equal to B, try to find out minima of Jx, and then there will be an iterative method for doing this. So, now we got the theorem that Jx is equal to x half of x transpose x minus x transpose B, minima of Jx. So, the theorem basically says minima of Jx is at a point where Ax is equal to B. So, if we can find out the location where Jx is minima, that will point to a vector for which Ax is equal to B. So, we will look into the proof of the theorem. So, it starts with Jx is equal to half of x transpose x minus x transpose B, and for minima we must have the gradient of, because this is a multivariable function, gradient of j is equal to 0. The first order derivative is 0, and provided A is symmetric positive definite matrix. So, that at least if A is positive definite, the second derivative of j x, so nabla square j will be positive, and we will see it later. So, if minimum gradient of j is equal to 0 and A is positive definite matrix, then this will indicate the minima of j x. So, now we write j x is equal to half of x transpose A x minus x transpose b. If we expand it, this term is a particular row and of A, and it is multiplied with x I and x j, and then all these terms are summed up. So, this is a scalar. So, this is half of I is equal to 1 to n, j is equal to 1 to n, sum of A I j x I x j minus sum of I is equal to 1 to n b I x I. And if I take its derivative with respect to kth component of j, we get half of I is equal to 1 to n a k I x I plus a I k x k minus b k. Now, if A is symmetric, this has to be noted carefully. If A is symmetric, A I k is equal to A k I. So, this becomes I is equal to 1 to n twice A k I, half of twice A k I. So, A k I x I minus b I. Okay. So, for if I write gradient of j, that will contain all the vector del j del x 1, del j del x 2 to del j del x n, and each of these del j del x term is basically I is equal to 1 to k a k I x I minus b k, one particular value. So, when we will find for minima, our requirement was grad j is equal to 0 at j minima. So, grad j is equal to 0, each term will be del j del x 1 is equal to 0, del j del x 2 is equal to 0 up to del j del x n is equal to 0, which is sum of a 1 I x I minus b 1 is equal to 0. The next term is a 2 I, sum of a 2 I x I minus b 2 is equal to 0, so on. So, each row of del j is equal to 0, each row of this matrix del j is equal to 0 represents one particular equation, which belongs to the equation system A x minus b is equal to 0. So, this will finally give me that a 1 1 x 1 plus a 1 2 x 2 minus b 1 is equal to 0. Then a 2 1 x 1 plus a 2 2 x 2 up to minus b 2 is equal to 0, so on. So, this del j del x is equal to 0, or this equation system del j del x k or del j del x 1 del j del x 2 is equal to 0. This equation system will give me nothing but A x is equal to b, or b minus A x is equal to 0, which is A x is equal to b. So, for us, and this is only for symmetric matrix, because if it is a non-symmetric matrix, then I have to write half of a k I plus half of a I k x I is equal to 0. So, for a symmetric matrix A, gradient of j is equal to 0 actually represents the matrix equation A x minus b is equal to 0. So, for minima or maxima, that has to be decided from the sign of nabla square j is equal to 0, and j is equal to, so we got gradient of j is equal to A x minus b, right. So, second derivative of j or Laplacian of j will be the matrix norm of matrix A only. So, if A is positive definite, then tabula square of J is greater than 0, the matrix norm of A is greater than 0 and J has a minima. If J is negative definite, then J has a maxima, and in case J is singular, then tabula square J is equal to 0 or J has a saddle point. So, you can ponder upon the question that how a saddle point will be in a multidimensional space. However, like we call it in a 2D space, we get an inflection point if second derivative is 0. So, it is something like that. So, if A is symmetric, then we got gradient of J is equal to 0 is similar to x is equal to b, and if A is singular positive, A is positive definite, then nabla square J is greater than 0. So, at gradient of J is equal to 0, nabla square J is also greater than 0, that means J is minima, and there Ax is equal to b. So, we have to look into the case where A is a positive definite matrix and nabla square J is greater than 0, that means is where J has a minima. So, is a positive definite matrix, and that means J has a minima at that particular location where del J del x is equal to 0, and if A is a symmetric matrix, then this particular location where del gradient of J is equal to 0 represents the matrix equation A x minus b is equal to 0. So, if A is symmetric and positive definite, then x minus b is at a particular location where J has a J is x transpose A x minus x transpose b as the minima, and that proves the theorem what we started with, and further tells us that minima of J will give us the solution of A x minus b. The solution of a linear system with symmetric positive definite matrix can be found by minimizing the quadratic functional J, or we can write that J is equal to x transpose, maybe I will write it here, J is equal to x transpose A x minus x transpose b at x star J x star is equal to J x mean, then A x star is equal to b. So, if I can find out an x star for which J is minimal, that particular x star will give me the solution of A x star is equal to b. So, instead of solving A x star is equal to b, we can now think of finding minima of J x star, and this is if and only if A is symmetric So, this particular methodology we are discussing we are only discussing this for symmetric positive definite. So, later we should also focus how we can improve this to a general matrix which may not be symmetric, may not be positive definite, how we can improve this methodology for that particular case. However, at this stage we are only considering symmetric positive definite matrix, and we observe that solving the matrix equation can be substituted by finding out minima of a quadratic functional. So, our idea will be now, because we have seen solving matrix equation by direct iterative methods, and at the beginning of the class I tried to list out the issues with the direct iterative methods, where are they restricted. Now, our goal will be, instead of solving this using direct iterative methods, we will use an iterative method for finding out minima of J. Instead of solving x star is equal to b, we will try to find out how we can achieve minima of J, and the location where we will achieve minima of J, we will say that this is the location where A x star is equal to b is also satisfied. So, we will say that the solution now is posed as a problem of finding minima, and to achieve this in an iterative methods we will use something called a gradient based method. the method we will use called a gradient based method, and we will explore this method in the subsequent slides. Now, the question is how to find the minima of J. In this class, at least in this class, we have always discussed about matrices, how to do work with matrices, how to find out solution of matrix, when we can have solutions, etc. But now we are in a little different paradigm where we have to find out minima of a functional. It is little different than what we are doing in the matrix equations. However, if you can remember the idea of symmetric positive definite matrix, when we discussed that, we have looked into minima of a functional, etc. So, now our question is how to find this minima in practical application. So, given when, for example, when I am trying to find out a minima, I have a function and I have to see where the function is minima. So, I will start with the value of the function. If I am going in the right direction, I am approaching towards minimum of the function, because it is a continuous function which we are discussing with, I will see that the value of the functional is reducing. It will reduce until it reaches a minima, and then it will increase. So, if I am going in an iterative method, say I am going in a trial and error method, I found out a value, a particular value of J, and next hit I find out another value of J. If this is reducing, then I am approaching towards the minima. When I have approached the minima, del J del x is equal to 0. So, at that particular location, if I change my primary variable little bit, there is no change in the value, but later I will see that the value of J is increasing with change in the primary variable. So, I will start with a value and I will see if the value is reducing, then I am approaching towards minima. And in order to reach minima, first I should see that the value of the functional is also reducing in the fastest manner. So, we need to see when the value is reducing and how we can reduce the value as fast as possible. So, we will look little bit into vector calculus. Given a function f and a unit direction vector g, the directional derivative of f along g is given by gradient of f dot g, and this is directional derivative means rate of change of f along the direction g. If g is along gradient of f, then g is an unit vector. So, gradient of f dot an unit vector in that direction, and that is the maximum value of gradient of f dot g, and this value is same as gradient of f. So, this is probably straightforward, that gradient of f dot g is basically its magnitude is gradient of f into g into cos theta. If theta is equal to 0, that means g is along f, and mod g, g is a unit direction vector. So, mod g is equal to 1. So, this is gradient of f into 1, and this is the maximum value of gradient f dot g, because if theta is non-zero, then there is this is theta is or cos theta is always less than 1, and this is a smaller value. So, given a function f and a unit direction vector g, the directional derivative of f along g will is f grad f dot g, and grad f is the maximum value of reduction of change of f along any of the direction, is maximum along the direction of grad f, and the maximum value is grad f. So, if we start from an arbitrary value of j, we should move along minus grad j, so that the reduction is, if we go along grad j, the rate is maximum. So, if we go along minus grad j, the rate is minimal, or the reduction is maximum. So, if we will start from an arbitrary value of j and we will move along gradient of minus of gradient j, so that j reduces at the fastest rate and it will reach its minima. So, if there is a j minima in this 2D space anywhere, and this is a j isocontour. Now, I start from one particular location here, because this is an iterative method, I have to start with something. I start from this method and I have to reach j minima. So, how should we go? I will see that in which direction j is reducing fastest, and the reduction is along gradient of minus j. So, I will move along from starting from some value x here, I will change the values along this line and see where the value is minima, because it will reduce fastest in this particular direction. Now, when I am in this location it is reducing fastest, but when I came to here then j has been changed. So, minus grad j is probably different, it is not reducing in the fastest way. So, it might here it is not reducing in the fastest way, it might not ever reach j minima, we will see later. So, you have to use an iterative method for that. However, if we start from one particular point, I have to go along minus grad j. So, the reduction is fastest. So, and the question is, so I know that I have started from an arbitrary point, I am going along minus grad j and I have to come to j minima. How should we reach that? So, if we move along this particular line, we might not be ever able to reach the j minima, because along this line j is first reducing, and then we can see if we keep on minus grad j, we can see that it is clearly missing j minima. Starting from any arbitrary j value, we will possibly never reach j minima. We will reach j minima in only in one case, that is the functional of j is a perfect circle. So, if we start from any point, the normal should take me to the center, but if it is not a circle, if it is an ellipse and I start from somewhere here, the minima is here, I will never reach the minima, I will go somewhere else. So, it probably never reach the minima. However, we can see this if we draw, this is the j isocontour, that means j is constant here. So, minus grad j is normal to that. So, we can see that up to certain level j will reduce, because j is initially reducing here, and there will be a local minima on this. We will probably go up to there and then see how we can again move. So, we need to change the search direction and approach iteratively. We will see, we will go along minus grad j and reach to one particular level, and then again I will calculate the new minus grad j here and move along this direction. I will probably again reach somewhere, from there I have to again calculate minus grad j and move along that direction, that is the iteration technique necessarily here. So, you need to change the search direction and approach iteratively, and this method is called the gradient search method. In the next class, we will look into more detail of the gradient search method. Thank you.